Okay, it seems happy temporarily. Let's see what's going to go on. So you have to have three things happening in order for work to be done. And they're not three things that you would... What's up with that? Sheesh, I think this thing is possessed today. All right, so we're going to get rid of this garbage here. Dadgum, that was whack, wasn't it? Okay. So those three things are, there has to be a force applied. It has to act through a distance. And it has to have part of it acting in the direction of the motion. Okay? So those are the three things. So if you go back to me talking about you thinking about studying physics, you had your pencil, you applied a force in the direction of motion, right? So you did do work in terms of physics, but it was a very minuscule amount. You were probably very tired when you got through your assignment simply because you'd used so much brain. Okay? And thinking, and it does get tiring. But the physics definition, you always just simply apply a force through a distance. Okay? Now let's see if it'll let me advance. Of course not. That would be too easy. Okay, so when we look at that right there, here is a lazy person leaning against the crate. He's shoving it. Hopefully he's going to try to move it, but no work is done there. Here the boat is pulling him across the water, so work is done by the boat. And here this young lady is mowing the lawn. Okay? Now as she mows the lawn, she does work, but I want to look at that because this is kind of a unusual question for a lot of folks. A lot of us haven't seen lawnmowers like that in a long time. Maybe never. Maybe your grandparents. Most of us ride our lawnmower. Okay? So there is a force applying and acting in the direction of motion. This is it right here. Okay? That's it right there. Bless you. So we're going to have to find that component of the force, but you've been doing that for 8 weeks now, so hopefully that won't shock you any at all. Shouldn't be any big difficult thing for you. Now the cool thing about work is that work is a scalar quantity, which means we don't have to worry about the magnitude and the direction. That makes life a lot easier for a lot of folks. They tend to like work and energy a whole lot because they are scalar quantities and it's a lot simpler to work through. Okay? Now, I just mentioned the fact that work is a scalar quantity. Okay? So I don't have to worry about the magnitude or direction. Here is my equation for work. Now I'm going to use a D here. That dot is a dot product. You don't really care about the fact that that is a dot product. One day when you take an engineering physics class, you will care greatly about that. But for high school physics, this is the equation you want right here. F cosine theta times R. So as this child is pulled across the snow with a rope at an angle, this is the force that's actually accelerating her. Yes, sir? Yeah. I would definitely use a D. I don't use R's, and you'll be a little confused. Okay, here's the dad here. He's exerting a force. She's moving in this direction, so I need to know how far she moved in that direction. Very easy to do. This is not difficult stuff at all. When we look at the area under a curve, if you have a force versus displacement, and it's kind of not shown here, but this is my distance. If you have a force versus distance graph, the area under the curve is the work done. Area under curve equals the work done. So if you look at this, even though it's not a curve, we call that our line or our curve. All you're really looking at is a rectangle there. Would you agree? How do you find the area of a rectangle? Base times height. If I did something like this and asked you to find that area under the curve, you would just tell me 1/2 base times height because it's a triangle. Everybody okay with that? So this comes in handy to know. All right. F force versus displacement graph versus BS. Okay. When you learn calculus, you won't have these nice, neat straight lines that I showed you on the previous slide. You'll have a function that might look something like that. And they will ask you to find the area under the curve. Well, you can't get a nice, neat shape. You can break it into strips, but you still see that you have a little bit of funkiness here that you're not accounting for. Everybody agree? So what they're going to teach you is they're going to teach you integration. You're going to learn it next year in calculus. Nah. And integration is simply the sum of all the little pieces under the curve. And what Miss Witten's going to do is she's going to teach you how to take an integration of a function, and if you can integrate a function, and if it's a the right kind of a function, you're going to wind up with the area under the curve, and in this case, it's going to be the work done. Okay? So you will learn that. Just not yet. And I won't give you any that have crazy curves to them. You can guesstimate. And we kind of did that, didn't we, when we did another graphing worksheet back in the first 6 weeks? The curve was kind of funky, and I told you to just kind of guesstimate. But when you learn to integrate, you don't guesstimate anymore. You know what's going on. Notes? Everybody agree? You would be wise to have a calculator. Does everybody have a calculator? What's going on with this problem? Now, I can list my givens, which is what I did over here, or I can draw a diagram, and that gives me my givens. I know that I have a 60 Newton force. It's acting at an angle of 30 degrees with the ground, and I'm going to move this object 50 meters. Okay? So my work is equal to F cosine theta d. Well, I'm going to deal with this right here because that's just going to give me this force acting in the x direction. Okay? So I'm going to say, well, 60 newtons times the cosine of 30 times my 50 meters Okay, somebody check my math, because cosine of 30 is 0.866, and 0.866 times 3,000 I think is 2598, but somebody check me. And we'll fix it if we need to. Now notice that we have NMs right here. That's newtons times meters. That's also called an energy unit called joules. So either way you want to work with it, it works the same. All right, so here's my givens. I know that my work is what I'm looking for. I know that I'm going to lift against gravity, so my force is going to be mg. My force is 3 kilograms times 9.8 meters per second squared. So I'm going to get 29.4 newtons. I want to lift a distance of 40 centimeters, but I cannot leave it in centimeters. I want it in meters. Now, be careful here. Your theta, well, if you're lifting that way, what is gravity doing to you? Or doing to the object, I should say. Pulling it down. So what's this angle right here? 180. So the work done is equal to F d cosine theta. So I'm going to have 29.4 newtons. I'm going to lift at a distance of 40 centimeters or 0.4 meters. Now be careful on this theta because I think I might have made a mistake. If I'm lifting up and my displacement is up, that's a cosine of 0 degrees. Would everybody agree? Because aren't I acting in the, isn't my force acting in the direction of motion? Okay, so let's change that to a lovely 0 degrees. What's the cosine of 0 degrees? Anybody know? 1. Beautiful. So my work done is 0.4 times 29.4 times 1. So that's a 16, a 7, 11.76 Newton meters or 11.76 joules. Somebody check me though. Are we good there? Here we go again. Let's look at this one. A force of 200 newtons moves a 100 Newton block up a 30-degree inclined plane. The coefficient of kinetic friction is 0.25 and the length of the plane is 12 meters. All right, well that's all good, but now we need to figure out what they want us to do in Part A. Okay, well in Part A, it says find the work done by each force acting on the block. So here we go. So here is our 200 newtons. We're going to take it up the ramp, 12 meters. We've got friction trying to slide it down the ramp. And we've got this FGX trying to slide it down the ramp. There's my theta here. Here's my other theta. So let's do the work done by the 200 Newton force first. So 200 Newton force, W equals F D cosine theta, or F cosine theta D, doesn't matter. F is 200 newtons. I'm going to push it up. It's going to move up. What's the angle between D and F? 0. Would you agree? Because I'm pushing it up and it's going up in the same direction. Cosine of 0. And I'm going to move it 12 meters. So that should be 2,400 joules of work that I did right there, because a cosine of 0 is 1. All right, now let's see if we can find the work done by friction. So the first thing we have to do is we have to find the force of friction. W is equal to the force of friction times cosine of theta times D. All right, well, let's move over here and find friction. Friction is equal to mu times force normal. Mu is 0.25. Force normal is going to be this little rascal right here. Everybody agree? And if this is a hypotenuse that's 100 newtons, then this is going to be FGY, which is the cosine of 30 degrees times 100, which is 86.6. And a fourth of 86.6 is going to be 21.4 will go into 26. There we go. Done by friction. So the work done by friction is the 21.65 newtons. We'll talk about the cosine in just a second. And I'm still going to have it go 12 meters. Now, Garrett, if friction is trying to slide it down but I'm moving it up, what's the angle between F and D? 0 is if they're in the same direction. Now they're in opposite, so what's it going to be? It'll be cosine of 180, which is definitely negative, because cosine of 180 is a negative 1. So now I want to multiply 21.65 times 12, and that's going to give me 25 point something. Somebody want to do that for me? What do we get? Bless you. Oh, hello, Miss Walker. You're not even close. 259.8. Now, what's the cosine of 180? Negative 1. So I'm going to put a negative sign in front of here, and I'm going to call it joules. I need to find the work done by the force FGX. So the work is going to be FGX times a cosine of theta times D. So I'm going to go over here and calculate FGX. All right, so here's my FGX. I'm going to plug in 50 newtons. I'll come back to the cosine in a minute. I'm going to move it 12 meters. No, we're still on part A, babe. Okay. All right, now let's talk about this cosine of theta. What direction is FGX acting? Down the ramp or up the ramp? Down the ramp. What's the direction of the motion? Up the ramp. So what's the angle between down the ramp and up the ramp? So that's going to be cosine of 180 again. So I'm going to get the work done is negative 600 joules.